Okay, so welcome everyone to the first informal seminar for the Astrophysics series here at the IAS. We're very pleased to have the semester being started off by Kohta Murase. So Kohta got his PhD from Kyoto and then spent some time at the Ohio State University and as a member here before going to Penn State, where he is now associate professor of physics and astronomy and astrophysics. He also has an affiliation at the Power Institute. Kohta is an expert in high energy astrophysics and particle astrophysics. And today he'll tell us about the multi-messenger view of high energy neutrino sources.
So thank you very much, and for giving me an opportunity to talk about the high energy neutrinos. And I think I think the last time I gave a talk here is actually almost 10 years ago. And this is exactly the time when the ice cube neutrinos were discovered. And I think that it's a good time to give us some overview of what happened in the 10 years. Okay, so I'd like to start with an introduction. So neutrinos one of the elementary particles which are electrically neutral and a lepton. And they interact with matter and radiation weak interaction that people often call the ghost particles. And the neutrinos from the space are important for both astrophysics and particle physics. And the good example is actually the come from Nobel Prize, right? So the detection of neutrinos for supernovae for the sun, then basically they enable us to study the very dense environment, which cannot be simply studied by electromagnetic observations. And then the neutrinos can be used as a probe of particle physics. And then the Snow experiments, supermassive, and the other neutrino detectors, they actually measure the neutrinos. And then they try to see the flavors. And eventually this leads to the discovery of the neutrino oscillation, which gives the evidence for the neutrino mass. And this is actually very important for the particle physics people. And then when the Kajita-sans won the Nobel Prize in 2015, then because the supermassive candidates that measure the neutrinos and the atmospheric neutrinos that are produced in the atmosphere, and then in this case, the cosmic rays that matter, he says that I want to suck the neutrinos, of course, but since neutrinos are created by cosmic rays, I want to suck them. But the cosmic rays, actually something we don't know where. And then this origin of the cosmic rays is a century-old puzzle. We see the cosmic ray spectrum over wide energy range, more than the 10th order magnitude in energy. And roughly speaking, we see the power law, but if you look the spectrum very carefully, then we start to see some structures. Actually, it's not so easy to see from this plot, but actually the spectrum is actually changed from 2.7 to 3.3, and eventually you have a hardening around the 3 EeV. EeV is a 3 times 10 to EeV is a 10 to 18 electron volt. So actually you have a steepening and hardening that we often usually call the knee and ankle. And then questions that especially if people call the cosmic rays above the 3 EeV, that we call the ultra-high cosmic rays. And people believe that cosmic rays up to the PeV or 100 PeV come from galaxies, our Milky Way. Then people think about supernova remnants or other sources. And then, but however, ultra-high cosmic rays are difficult to confine in our Milky Way. The people believe that they come from the extragalactic space. And the question we have, how is the spectrum formed, where the transition happens, how are cosmic rays accelerated, how do cosmic rays propagate? We have many questions, and then in order to address these questions in any way, we probably need to know the origin, what is the origin. And then especially the ultra-high cosmic rays are one of the big mysteries, because if you want to produce ultra-high cosmic rays, okay, so the largest collider we have is the Large Hadron Collider, of course, and the energy we can achieve is about 30 TeV, which is about 3 × 10⁻³ electron volt in the center of the mass frame. And then, but if you want to think about the ultra-high cosmic rays, okay, if you want to produce ultra-high cosmic ray by LHC magnet, you need to develop an accelerator with a Mercury orbit. Yeah, alien can do that, but maybe, it's difficult for us, right? So far. So even for space, not so easy. So you probably need a monster accelerators in order to produce tiny cosmic rays. One of the primary candidates actually the supermassive black holes. And I just take the picture of the M87 and agents. And then indeed we see that we know that there's a supermassive black hole, and in the center we see the powerful jet, and with the kiloparsec, and then such a powerful jet could accelerate the cosmic ray to ultra-high energies. However, this is a speculation, and then if you think about the candidates, people think about different possibilities, and then at least we don't know little, but at least we have a necessary condition. In order to produce ultra-high cosmic rays, at least you need to confine the cosmic rays in the system, and the Raman radius of the particles has to be smaller than the size of the system, okay? And then this is actually so-called the Feynman-Pierce conditions, and then the x-axis is size, and the y-axis magnetic strength. And then if you actually examine whether ultra-high cosmic rays of 10 to 20 electron volts can be confined. And in the system, actually not so many sources actually can satisfy the condition. So you use many levels, but essentially these are classified in the most extreme accelerators. The magnetars, gamma bursts, active galactic nuclei, galaxy clusters, these are among the most extreme objects in the space, right? So the magnet are the strongest magnetic fields, and the GRB is the most luminous object in the universe. At least you need something extreme and then to produce the ultra-high cosmic rays. However, we have actually you could think about, oh, in this case, you can try to use the cosmic rays then, but the story is actually not simple because the cosmic rays are mostly charged particles. And then usually we don't know the magnetic fields very well, and then they can be intervened by the galactic magnetic fields and extragalactic magnetic fields, especially extragalactic magnetic fields are poorly known. And it's difficult to know the direction of ultra-high cosmic rays. So that therefore the people actually think about using neutral particles, which are gamma rays and neutrinos. And then gamma rays are fine, but there's one issue because the very energetic gamma rays actually start to interact with the cosmic background radiation field, including the CMB and external background light, and coming from the optical and infrared. And a very energetic gamma rays interact with the CMB or EVF. You have two photon annihilation, they're producing electron position pairs that they cannot directly be observed. This is happens in the above TeV. For example, if you look at this energy, if you access the plot to the energy and distance, so for example, if you think about 10 to the 12 electron volt gamma rays, basically the gamma rays can propagate only about 300 megaparsec. And if you think about the PeV, PeV the 10 to 15 electron volts gamma rays, basically they can only propagate 10 kiloparsec. So that we can only see the galactic sources. So, but the neutrinos actually do not suffer from this problem, right? And then basically the neutrinos can be are powerful to actually probe the distant universe in principle. Okay, then how can we detect the neutrinos? Of course, this is not so easy, but actually people already the proposal actually made in the many years ago, 60s. Okay, so several people actually proposed, and then the idea is actually to use the water, and then think about a lake, or you can actually put the water in the tank, and then actually when the neutrinos come coming, and the neutrinos interact with water and make the charged particles. And charged particles emit Cherenkov radiation. The Cherenkov radiations can be detected using the the optical detectors, right? And then this is the idea. And then, however, but the neutrino detection is actually not so easy. The proposal was there many years ago, 60s, but simply because neutrinos interact with matter with big interactions, and then you can estimate how big should detector be, right? And then so the cross-section neutrinos actually, roughly speaking, the Fermi constant square, the energy basically is more epsilon s. And then this increases actually energy. So if you think about 1 PeV range, the cross-section is order of 10 to the minus 33 centimeters square, which is still much bit smaller than the Thomson cross-section, right? You can estimate how big the detection should be. And if you think about the typical flux of the cosmic neutrinos, please take this number as a Fisher value. And then you know the cross-section sigma, and then you can estimate the volume to see the 10 EBIT per year. Then just the order of magnitude estimates tells us, in order to detect neutrinos in a reasonable number, that you need a basically kilometer cubic volume. So the proposal there, but building such a big detector was not so easy, right? That's the reason why it took time.
Why the cross-section increases with energy?
Oh, that's here, because neutrino cross-section is actually just you think about the charge current interactions. Then basically you think the four contact interaction, basically the dimension analysis, right? And then basically the GF squared, this is the dimensional energy square, and the energy defines 4, right? And then simple actually Mandelstam minus S is actually the energy of P, right? And then because you're thinking of the neutrinos are almost massless, you're thinking the proton is actually quite massive, right? And then in this case you have energy is actually S is actually proportional to the energy that you have. You get cross section increase with the energies in this energy range. And eventually the structure function of the protons actually start to be important at some energy. That's the reason why that cross sections actually energy dependence is weaker at high energies.
So what is X?
Oh, the X are anything. I'm going to explain now. So there are two things. Okay, so the how you detect the neutrinos. So when the neutrinos interact with the ice, then N is a nucleus. Okay, so then there are roughly speaking, we have two patterns. When the mu neutrinos interact with the ice, so proton or neutron, right, nucleus, and then basically you have muons because of charge current interactions, right? And then you have then basically the nucleus breaks up. And you have pions and a bunch of particles, then this is the X. And basically eventually cascade happened, and we have a hydraulic shower. And then you can also expect such interactions, and not only charge current interaction, but also the neutron current interaction happens. And then electron neutrinos, the tau neutrinos, basically they cause again, they can interact with the nucleon via charge current interaction with neutron current interaction, that you can produce the neutrinos, and in this case you have a hydraulic shower. But in the charge current interactions also happens, and you have the electrons and tau, and this actually is these charge electrons can be produced via charge current interactions. You have a hydraulic shower, and then the electrons also produce the electromagnetic shower. And then we can detect that basically the Cherenkov radiation from the charged particles, or you can actually just think of then in this case you have a shower cascade. In this case you have a tracks because the muons travel a lot, right? Muons actually you can travel and with a much direction with head. So that you have two patterns, and then this is actually the basic principle for the detection of neutrinos. So the IceCube actually, the build in 2010, then more than 10 years ago, it's completed. Basically, it's built in the under the ice and 1 kilometer depth, and then you have kilometer cubic volume detectors. You have many strings, and each string has many PMTs, optical modules, and then you see that the size of the detected much bigger than Eiffel Tower, right? And then if you think about, if you project an image of a shower in the Madison, it's something like this, okay? So this is the energy of neutrinos in the PeV, in the 15 electron volts. If you project this kind of shower, it's actually the size is something like this.
Why is it better to use ice rather than the ocean?
Oh, that's it's actually both are important. We have a pros and cons. And if you use the ice, actually the attenuation is actually smaller than the water. So in a sense, if you want to detect the neutrinos at the higher energy, actually the ice is actually somewhat better. But actually if you want to, but the ice is actually have the usually more scattering. And then in that sense, actually, if you want to improve the angular resolution, then actually water is better. And also the ice is actually, in ice cube is actually also the stable, right? Water is actually the, you need to be careful about the waves, and you need to think about the environment. And yes, the once you put the detectors, it's fixed. It's the one thing.
You also don't have to worry about curious sea creatures.
Yes, but this is actually more actually you can measure the bioluminescence, right? Bioluminescence, and but usually this has a characteristic signals, and of course you need to study the bioluminescence. But now the people actually handle. You can this actually the chemistry net or these others people actually publish the paper on the bioluminescence for echolocation. It's a kind of interesting.
So for the ice, do you need to worry about cracks and defects in the crystal of ice?
Oh, but this is much deeper. It's actually the pressure is super high, right? Because it's actually 1 kilometer deep. The crystal is actually much shallower. It's much deeper. Usually, the more important thing that in here is actually because of high pressure, and in this region actually even ice is almost clear. Even ice is very clear because of high pressure. It's more, it's more transparent than the ice we can see here.
Okay.
Yeah, but still, in principle, you have a dust layers because then sometimes actually dust can be important. Or when you put the string, is actually that you need to drill with hot water. But when it freezes, it can create a bubble, and you need to be careful about the ice properties. And actually, ice properties is actually called some systematics.
Did they pull up ice cores from this to measure stuff?
Sorry?
Like when they did the drilling, I know that in other contexts, they pull up ice cores. They go down and they just pull up chunks of ice and measure properties like the atmosphere, however many thousands or millions. Do you know if they did that for this? Like how did they drill?
Oh, just use a hot water, but I don't know yeah.
And are they frozen in now because the ice?
Yes, it's frozen, of course. Then frozen, then complete frozen. Then once you put
The tube you make will be just.
Yeah, then once you put these frozen, then everything fixed. You cannot remove more any longer. If they're broken, no way to.
One day they will appear in the ice sheet in Antarctica somewhere.
yeah. So the water in principle you can replace. So if they're broken, you can actually take off, but usually they don't do this. Okay, so good. And then now actually this is our distribution neutrinos. Now the 10 years, they actually we have a lot of events, more than 100 events, and then roughly speaking, the distribution of neutrinos is consistent with isotopic distribution. You can see some deficit here because of very energetic neutrinos actually start to interact with Earth, matter in the Earth. Basically, because Earth screens the high energy neutrinos, then you start to see some deficit. But once you correct these, the basic distribution is consistent with the isotopic distribution. And we don't see any excess in the galactic plane, then we believe that this is consistent with the X-ray technology. And then we also measure the spectrum, so that I told you that there are two modes, right? You can measure neutrinos using the tracks and using the muons, and this is actually showing the band. This is actually neutrino spectra measured by tracks. And you can also measure neutrinos using the showers. The showers are mostly created by electron neutrinos, tau neutrinos. And then in this case, this is actually is indicated by the data points, okay?
Is that dip statistically significant in the shower events?
Not yet.
Okay.
Actually, it's still there, but yeah, I think that it's not like a 3 sigma, no.
You mean like a 2 10 to the 8?
Yeah, here, it's actually the
Or I mean,
Yes, this
at
one.
like 10 to the 5. to 10
Yeah,
to the 6.
this one. Because this is actually the, this here is actually 2 events, this is 1 event.
Okay.
Yeah, then, so in this sense, actually, so far, it's not significant. So the average.
So the upper limit you draw here is for 1 sigma. Or for 3.
Oh, this is 1 sigma, yes. I think the upper limit is probably the 90% or something like that, yeah. I need to check, 90%, 95%, you know, I forget. Yeah. And then we see the spectrum, then you see that the spectrum is more consistent with it's possible to expand the spectrum the consistent power, and the important thing is that the flux level is order of 4 times 10 to the minus 8 GB per cent square per second for hydrogen. And the spectrum is now seeing the 100 TeV range. And we don't see any ultra high neutrinos in the EV, in the 18 or, you know, ultra high neutrinos are not detected. Okay, and then by looking for the neutrinos are produced by because the showers are mostly created by electron neutrinos and tau neutrinos, and the tracks are created by mu neutrinos. So by looking for the ratio, you can actually have a information for the flavor ratio. And then if you think about the neutrino oscillation, so in the standard case, neutrinos eventually mix, each flavor mix. And you expect that to 1 to 1 to 1 on Earth. And then so far, this is the result, right? You see that the contour is quite big. So the many possibilities are allowed, and data is actually consistent with a 1 to 1 to 1. But at least we can say that crazy scenarios, like all the neutrinos are electron neutrinos, such a possibility is already displayed. So basically, neutrino observation can tell us about the flavor. This information is actually kind of important for the people who are working on the beyond the standard model. And then one special event was also reported. So actually the anti-electron neutrinos interact with the electrons, and which can make an on-shell double boson. And double boson decays, and such an event is actually called glacial resonance, and which was predicted again the 59, around 60s. And such an event was also seen. Of course, it was about 2.3 sigma because just one event, but this event actually quite consistent with the glacial resonance event. So the impression that we have is more basically ice cube can be regarded as a detector for the anti-electron neutrinos. In the sense that that's kind of interesting.
How many such events do you expect?
Just one. Oh, eventually ice cube Gen 2, if you have a future detectors, we can have one pair in the 1 year. Yeah, depending on spectrum, yes. So I would say the Q per year. And if you have 10 years, actually the dozens if possible. Okay, then the big question we have is that where do neutrinos come from, right? So this is actually what I present is the all sky neutrinos. So basically the neutrinos actually come from the entire space, alongside, that you can expect many sources. Then people think about the different kinds of sources. And then how such a neutrinos are produced. Actually, the people in this case, we usually think about two processes. The very energetic cosmic rays interact with photons that we call the photomeson production process or P gamma process. And such a process is important for the energetic sources such as gamma bursts, AGN, because they provide a lot of photons, right? And the cosmic rays interact with photons, and you can have pions, charged pions, eventually decay, you have neutrinos. And then if you think about the galaxy or galaxy clusters, in this case, they have gaseous environments, and the protons can be confined in the system for many years. And then the confined cosmic rays hit the gas and produce charged pions. Again, you have neutrinos. And then in this case, we call the PP interactions or halo-nuclear interactions. These two processes are the primary process to produce neutrinos. But you also have gamma rays, right? Because charged pions produce neutrinos. Charged pions actually decay into neutrinos, but you should also have neutral gamma ray, neutral pions. This is unavoidable in either PP or P gamma case. And I told you that you have gamma rays, but in this case, the story is a bit complicated because the gamma rays actually, as I told you, the gamma rays interact with the cosmic back radiation. Then you have an ultimate cascade. But energy gamma rays do not have to be observed on Earth as they are. So you need to think about this electron cascade process as a set. So taking into account this, and then you can actually think about a multi-messenger approach. So basically, you can actually try to make a connection between neutrinos and gamma rays. Then for gamma rays, you need to think about these actually the cascade processes always. So what do you have now? Now that we have messengers from cosmic rays, neutrino, gamma rays, and then one of the important implications of the observation is that if you plot the all sky flux as a function of energy, so you see you have neutrinos, cosmic rays, and gamma rays. If you compare the energy flux of the ultra-high cosmic rays around the 10 to the, above 3 AeV and ice cube neutrinos and Fermi gamma ray background in the sub-TeV range, okay, within the one order magnitude, okay, they're more or less comparable. Okay, so the energy generation rate density of these particles is actually more or less comparable within the one magnitude. So that you might think about maybe the three messengers may have a connection. So that actually is a natural, guess, right? Of course, there's no proof, but I think that it's a kind of interesting fact. So, but we don't know the neutrinos, original neutrinos, cosmic ray, but we already have clues in the gamma rays. So that if you look at the gamma ray sky, then yes, we see the galactic planes, and sorry.
So in the last plot, the gamma ray energy does not correspond to the cosmic ray energy, right? They are not.
Yes, particle energy is different by more than 10th of the order of magnitude.
So we do not, this gamma ray is produced by that energy range for cosmic rays.
Yeah, actually, that's the point. Actually, in principle, they can be connected because energy generation density is actually comparable. So in principle, if the cosmic rays actually produce and put some interactions, basically gamma rays eventually cascade down. In principle, you can make a connection, which I can demonstrate later. So basically, that's the point, right? So the energy flux is more energy generation density comparable, even though the particle energy cells are very different by more than 10th of the magnitude energy. So if you look at the accelerated gamma sky, there are many AGN. We actually now have more than 3,000 AGN, found in the Fermi gamma satellites. We know that the blazars and the fused jets that point to Earth are dominant in the accelerated gamma sky, especially above 10 GeV. We don't know what's going on in the below GeV, but above 10 GeV, we are actually at least 50% comes from blazars. So in this sense, it's quite natural to ask that, the blazars may explain the neutrinos, right? Then people actually look for. Then because the blazars are so bright that you can actually do the stacking analysis, right? You can stacking analysis, and then you can actually estimate the contribution to the blazar contribution to the neutrino flux. However, the answer is actually not simple, because basically the stacking analysis, actually the result says that the blazars are likely to be subdominant in the neutrino sky. And then you can also use the anisotropy information by looking for the clustering in the neutrino sky, but this actually gives a similar result. So that's somehow the grazer is actually the dominant in the gamma ray sky, but it's unlikely to be dominant in the neutrino sky. And then same story is actually applied to the energetic sources such as gamma ray bursts. Gamma ray bursts are so bright that you can do the stacking. We know that the contribution of gamma ray bursts to the neutrino flux, ice-cube neutrino flux, is less than 1%. We have strong limits. And that is why one of the possibilities that we could think about the reservoirs is one of the possibilities is actually the cosmic reservoirs, in which the cosmic ray that can be confined in the galaxy clusters, the star-burst galaxies. Indeed, such a possibility are very interesting that in the sense that it was predicted before the discovery of ice-cube neutrinos. So one of the possible papers, possible idea is actually the Loper and Waxman. And then we have some papers, and basically in this idea is that the cosmic rays are confined in the magnetized environments, and the confined particles actually create the neutrinos by interacting with gas. And then you have neutrinos, and escaping particles actually can produce the cosmic rays. So the situation like this, if the AGN would have the cosmic ray accelerators, and the cosmic rays actually propagate, right, like this. And then you have creates pions, and the neutrinos actually come with the go straight, right? Gamma rays. But the cosmic rays actually is the charged particles actually they actually interact with magnetic fields. And in principle, in this picture, it's possible to have three messengers simultaneously. And then that's actually interesting. So that in the sense that indeed it's possible to explain the three messenger data simultaneously, because confined cosmic rays can explain the neutrinos, and escaping cosmic rays eventually contributes to the cosmic rays observed the Earth, and eventually the gamma rays cascaded down that contributes to the Fermi range. So that's actually one of the possibilities to give you a kind of unification pictures of the messengers. However, so this looks nice, yeah, in just a first glance, but actually, unfortunately, probably the universe is not so simple as usual. Okay, if you just look at this data, that look fine, but even for neutrinos, we already start to see that, what's happening here, right? You already start to see that, okay, what's happening here. And then now I think that this is actually we have more statistics in the neutrino data below 100 dB, and then this actually seems to be here. Basically, this model cannot fully explain the neutrino data. So the unification looks nice, but it's not simple as it is.
So there are like parameters like the magnetic field or something you can tune.
No, but this is actually magnetic field is actually important to determine the confinement time scale. But for this model, if you actually neutrinos gamma ray flux are almost comparable. So in a sense, if you try to explain the data, basically it's a fix almost. And then magnetic field is actually important to actually determine the confinement energy. And basically, if the magnetic field is actually too small and it cosmic rays escape, basically you cannot explain the neutron data or something like that.
Okay, does the magnetic field need to be independent?
This is dependent on objects, but if you think of the galaxy clusters, basically that we can use the magnetic fields used for the galaxy cluster, like a 0.1 microhertz.
Sorry, one last question. How many what proportion of AGN can be found in these reservoirs?
I think that usually the one AGN actually found in the galaxy cluster.
An order one proportion?
Yeah, one is actually found. And then also it does not have to be active now. Yeah, because basically the AGN activity actually is much, but in this sense, actually, maybe if the AGN is active in the giga year ago, then it should be wide.
So are we considering the AGN is also the source of cosmic rays?
Yes, I think so. This scenario is actually the agents that provide cosmic rays and accelerate cosmic rays. And then basically the galaxy clusters that serve as observer. So any question? Okay, so then now that I'd like to ask what can we say in the more general, right? It's that kind of, it's good to, it's interesting model, but it doesn't have to be the case. Then one general exercise we can do is that just comparing the neutrinos and the gamma ray data. Because the relationship between the neutrinos and gamma ray is robust. You cannot change. This is determined by particle physics. So that if I want to explain the neutrino data here, then whatever you use, like PP over P gamma, the gamma rays are created, and then you can robustly calculate the gamma ray cascade if you assume that gamma ray source is actually transparent. Okay, this is something that we can do as a minimum exercise, right? And if you do this kind of calculation, what we can find is that no matter what you do, and for example, thin line is actually the kind of more easy to understand. And if you want to produce the neutrinos, explain the neutrinos, and the cascaded gamma rays are indicated by the red line, then you find that the expected gamma ray flux actually overshoots the diffuse gamma ray flux data measured by the camera. You can more elaborate that you can do some statistical analysis, and you can find that the tension is, I think, around 3 sigma. It's a bit model dependent, but around 3 sigma. And if you actually add more components, and you actually tension is bigger. So this actually, what that means that if you believe the gamma ray data or the bifermi and STU data, and then if you assume that the source is transparent, then basically you actually violate the Fermi data. So that this implies that you need to invoke a mechanism to block the gamma rays. So we call hidden sources. So that's actually one of the implications that we can get from the diffuse data. Then we expect that such a hidden source is necessary. And then this is natural. So then I think that it's natural. Because, especially in the P gamma interactions, because if you think about the physics, P gamma interactions actually is you order to produce neutrinos, you need target photons, right? But target photons actually is also dangerous for gamma rays, right? Same target photons are dangerous. So that if you want to produce neutrinos and of the 10 TeV neutrinos, you need 100 TeV protons. And then target photons actually is required target photons actually kill the gamma rays in the GeV to TeV range, roughly speaking. This is actually determined the particle physics that I cannot change. So basically, it's the cross-section ratio is actually about 1,000 between the P gamma interaction and the gamma gamma interaction. If the neutrino production is efficient, basically gamma gamma production is more efficient. Gamma gamma annihilation should be more efficient. The gamma rays should not escape. In this sense, that if you think of the P gamma guy, then this kind of possibility is pretty natural. And then in this case, which kind of the source environment actually is expected. And then one of the interesting, promising possibilities that the vicinity of supermassive black holes. There's another possibility that actually is some jet embedded in the supernova that we call chalk jet. And then these actually, we think that these kind of hidden or basically dense environments are promising sites for the neutrino production. This is actually our expectation. Then the question now, the next question is that do such hidden sources really exist, right? This is actually these implications are obtained from the diffuse data only. And then now I think the answer is yes. So now the last year, so the ISQ actually made an announcement, right? So the new papers are published in their science, and ISQ actually reported the evidence for the neutrinos from the NGC 1068. NGC-1068 are one of the famous, probably one of the most famous spiral galaxies, and we know that they're actually the AGN in here. It's a so-called type 2 saphers, and it's a very actually thick environment, and it's a compton thick. And then the armor or infrared telescopes actually this is actually infrared image and obtained by the interferometer. So this is the neutrino data, and then IceCube actually look for the neutrino point sources, and then basically the hottest spot in the neutrino skies actually turns out to be the direction to the NGC-1068. Then you can actually you can try a different search. The one of search is actually they use a catalog search, so that they prepare the catalog of the 111 sources, and then this is predefined, and then they look for the brightest source in this catalog, and it's again turned to be the NGC-1068, and then they using the posteriori, and the significance is actually the 4.6. So it's actually kind of impressive, right? So because this is neutrinos, and this is the NGC-1068, and you see that you can see that the excess of the 80 event excess towards the direction of neutrinos. This actually data point actually obtained using the neutrino data. So single source. It's actually kind of impressive. So then they can also provide the spectrum. Here is a spectrum, and here is the energy and energy flux. And the shaded range actually the IceCube flux. And the spectrum is soft in the TeV range. And then basically they see the neutrinos in the TeV to 10 TeV range. And then one fact you can learn is that the neutrino flux is larger than the gamma ray flux measured by Fermi-Rad, and the upper limits reported by the MAGIC telescope, right? So in these, just from this plot, you see that neutrino is actually, this source is a hidden source in the sense that you have to mask the gamma rays somehow, right? So that's actually the one evidence for the hidden source simultaneously. Then the question is that where, then how that such neutrinos are produced. And then people actually, the NGC-1068 actually known to be the starburst galaxy. And then people actually think of the starburst model, but if you think of the starburst model, you expect that the neutrino flux and gamma flux are comparable, but such a model is impossible because neutrino flux is much higher. So probably the most promising region is vicinity of supermassive black hole. So that if you actually look at the vicinity of supermassive black hole, and then you expect the accretion disk, and then you have a corona, so that you have a optical UV radiation from accretion disk and X-ray from the corona. These actually provide ideal target photons for the cosmic rays, and then the protons can efficiently interact with these photons in such dense environments. And then this is actually region kind of interesting that in light of the recent developments in MHE simulations. And I show that one of the papers team. So, okay, then that's actually the most favorable region. Then how robustly can we say that the neutrino emission region has to be such a small region, right? Then again, I can make some general argument in the model independent manner, okay? So this NGC-1068, we have a measurement from the infrared and X-ray, and we also have an optical observation. And all the estimates indicates that volumetric luminosity is the order of 10 to the 45 electrons per second, within 1 on the magnitude or something. So the Eddington rate is pretty high, it's actually over order of 0.3 or something like that. And then X-rays actually indicates the luminosity of X-rays. Actually, new study has a measurement, the luminosity of X-ray over 10 to the 44 or several times 10 to 43. And then these actually that provide the target photon on the neutrinos and the gamma rays. And you can actually calculate the gamma optical depth as a function of energy, and assuming that for the different emission radius. So the ballpark that just order estimates. So that if you want to block gamma rays, because you have to block the gamma rays during the GeV range, you can do the back envelope estimates. If it requires the optical depth is larger than 10, then basically you can get constraints. Emission radius must be smaller than 30 to 1 Schiller speed radius. So the just simple estimates implies that the neutrino emissions actually has to be small. So in order to not to violate the heavy data. So you can do the check this with a more detailed calculation. So because I can repeat the exercise what I showed for the diffuse flux, but I apply now this exercise to the single source. So that again, the story is the same, right? So the neutrino data is given. So that if we want to explain the neutrino data, whichever the PP or P gamma, you know the gamma ray flux, and the gamma ray flux is eventually cascaded down, and you can solve the kinetic equation. And then you have to not to violate, you have to be consistent with the observed Fermi data, what the emission radius should be. And then the constraints, okay, if the emission radius is large, for example, you can see that the gamma ray is actually the escape, high energy gamma rays can easily escape and you violate data, right? So for example, 10 to the 4 Schwarzschild radius, you see that this expected gamma ray is actually already exceed. And you have to actually suppress the gamma ray flux. You can actually get the constraints, and again, you can confirm the result of the back-over envelope estimates that the emission radius is likely to be smaller than 32 Schwarzschild. Such a small region is actually also favorable for the neutrino production because you can also achieve the calorimetry of the cosmic rays. Basically, if you put the cosmic rays are essentially almost depleted for neutrino production. So such a region is actually the most natural in a sense. So which is a model independent argument. Then, now that I can think about models, this is actually the kind of speculative part. So that we don't know where the particle acceleration happens. The emission is likely to be happening in the very small regions. Then 30 Schwarzschild radius, 10 Schwarzschild is actually more or less the coronal regions or jet base. Then one of the possibilities that maybe particles may be accelerating the coronal region, some collision-less regions or jet base, and some people think about the fair fallback winds. Traditionally, I think people actually propose accretion shock, but now such a model is actually more or less excluded. And then now actually what happened here. And then we don't know that maybe the turbulence may be important, or shear is maybe important, the big connections or shock or whatever. That's actually open question. And then one of the topics, actually, possibilities that I'm interested in, actually, turbulence sections. That is why one of the purpose to visit here. And then well, for example, in the coronal region, the MRI happens and the turbulence is generated. And then this is actually a good site for the stochastic acceleration type 2 Fermi mechanism. And indeed, I showed that one of the simulations and using test particle simulation for using the snapshot generated by the MRI simulation. Then you can see that the particles are indeed scattered, and then it's possible to see that the particle acceleration in the turbulence. The nice thing of the stochastic acceleration is that time scale is actually consistent with the ice cube data. So in this environment, the most important cooling process is the base heteropipe production due to the photons from the disk and corona. And then second order Fermi acceleration is relatively slow compared to the shock acceleration, right? If you put a reasonable magnetic field unexpected in this environment, then you can estimate the maximum energy of protons, which is order 100 TeV, and which is actually consistent with the maximum energy of neutrinos around 10 TeV. So that's actually the good coincidence. In the sense, actually, I'm kind of it's kind of interesting to think about this.
Have spectral cosmic rays to constrain the acceleration mechanism?
Yeah, in the observational constraints.
Uh-huh.
Yes, actually, I can probably at least we have a constraint. The spectrum cannot be too soft until low energies. At least we have to cosmic sector has to be bumpy. Yeah, e to the -2 is okay, but if you cannot be steep as 3, as up down to the low energies. Okay, so this is the speculation part, but now I think that I want to say that okay, this is actually the NC10 that now the promising source. The good thing is that such a source is actually also if this is the real actually the one of the ice cube sources, we should expect that similar source exists in the entire universe, right? And then these AGNs actually are NC10 like AGN actually are also possible to explain the all sky neutrino flux and by thinking of the high ratios, so very natural. So basically the basic problem of the 10 TeV neutrinos actually that can be explained by this component. Okay, then just I want to mention using 10 minutes so that now that actually which kind of test we can do observationally. Okay, so that this is actually very interesting possibility, but what is the testability? The good thing that this kind of the possibility can be tested in the more or less near future. Now that actually not only ice cube, but also the chemistry net biology is actually now almost ready. It's under construction. We are going to have neutron detectors in the using the sea and the lake, and the next generation detector like ice cube is also being primed. So NC1068 actually is if you look at the ice cube sky, NC1068 is actually one of the brightest in the X-rays, especially once you collect the X-ray absorption, because this is component secret here. So this actually explains why the NC1068 is the brightest in the northern sky. But if you actually look at the physics data, and then actually if you southern sky, then you have more interesting the X-ray bright sources. So then, for example, if you look at the chemistry net sky, actually there are more component situation, like as NC1068. And then maybe once you have chemistry net, and they can find more relatively easily. So if you think of stacking analysis, basically within the several years, still you need to wait several years, but within the several years, it's possible to achieve the 3 sigma to 5 sigma. So another predictions of this model is that because of energy conservation, then if neutrinos are created, and as I told you, the gamma ray eventually must appear somewhere, right? Then this is actually eventually the gamma rays must appear in the MeV range. This is unavoidable with the energy conservation. And then this is actually good prediction for the future MeV gamma ray telescope. So unfortunately, we don't have good MeV gamma ray telescope, but we have Amigo X or eAstroGam like future gamma ray telescope. Actually, this kind of component should be visible. So this is another test. And for this kind of model. Okay, so now that actually finished I would like to move on summary. So I don't have time to just mention about the transient, but probably I can skip to the conclusion. So first I gave you a review of the hydrogen neutrinos in light of the multi-messenger observations. So one of the important facts is that the neutrino energy budget is more or less comparable to the gamma energy budget and ultra cosmic budget. So where do they come from? The Brazier, GRBs, the brightest sources are seemingly subdominant, so likely to be subdominant. And the reservoirs, like a galaxy cluster stuff, are still interesting because they can provide some indication pictures, but at least the multi-messenger data analysis, and especially for the 10 TeV neutrino data, suggests that we need some hidden source population. And such a population is now indicated by the detection of the energy 1068. So this is indeed a hidden source. If you believe this data, the emission radius is likely to be very compact, let's say the less than 130 to 100 radial radius. Now, I don't have time to talk about the other agents emissions, and actually the IceCube actually reported the coincidence of the neutrinos with blazars flares and like a TXS 0506. And then now that since then we have more coincidence. Actually, we have several coincidences between the blazar flares and neutrinos. But I would say that the situation is very positive now, because always 3 sigma like coincidence, and usually if we do this kind of analysis and based on the multi-messenger data, basically the theory is not to be reconciled with the data very well. We have to invoke some complicated model to explain the data. And also that usually we have very severe energetic issues. So for example, this is actually interesting for the particle acceleration people, but if you believe this data, usually you need a very luminous power, very powerful cosmic luminosity has to be very large. So sometimes actually cosmic luminosity exceeds the elliptic luminosity. And then also the acceleration efficiency of proton is actually much larger than the acceleration efficiency of electrons. The ratio can be more than 300. And then I don't know how we can explain such a big cosmic luminosity from the first principle. This is actually the open question. So in this sense, actually, in order to solve this kind of problem, definitely we need a multi-messenger. We need to establish multi-messenger pictures and better understanding the multi-zone emissions are pretty important. So observation in the future is right because next generation detectors coming. Now, I just want to finish my talks with the word from the work. Okay, so one verse. So this is a book called John Barker. So it says that neutrino astrophysics may grow in a time as short as 1 or 2 decades, right? So when I gave a talk 10 years ago, that this is actually the first detection of neutrino happens in 10 years. Exactly now that we start to have some first evidence for the neutrino source. Maybe in the next 10 years. Maybe something different, I hope. So thank you very much for paying attention.
So for the last part of the talk, do we need to consider it is the P gamma dominates or PP to explain the gamma ray data? Actually,
in the NC1068, actually you can explain the data either PP or P gamma. And the P gamma case, it's relatively straightforward because we know that the target photons are provided by this kind of corona. PP case, actually, we need to think about the origin of the material. For example, if you think about coronas, and actually really depends on the accretion flow. So in the corona models, as far as I check that if you want to explain the neutrino data with a PP scenario, then the corona region is actually cannot be pair dominated. If they're largely pair dominated, then you start to have some problem in the parameters. So in this sense, actually, if the neutrinos actually, if we figure out neutrinos, maybe it might be used as a information to constrain the composition in the corona region. That's like one of the possibilities.
I think maybe you skipped, but is there, some chocolate jet scenario for gamma ray burst or collapses are rejected already? Or
not excluded.
So still worse.
Yeah, I think of course, diffuse, in order to understand the diffuse origin of diffuse flux, we need many steps, right? So far, shock jets actually, if the jets actually is buried in supernova, we don't see the gamma ray burst, and then basically the stacking analysis actually
Doesn't work.
yeah, work, but so far the constraints are not so strong. And basically still it's possible for them to explain the 100%. We had some stuff, we indeed tried the stacking analysis using the supernova data, but the constraints are not strong to exclude this possibility.
In the expected gamma ray spectrum from these hidden sources, is that coming from primary gamma rays or is that coming from synchrotron?
No, not the cascaded case actually, the no primary gamma rays. Basically, primary gamma rays are all dumped. So that basically the gamma rays are attenuated the pair production, the electron positons actually emits a synchrotron or even compton. Then either possibility actually exists.
Good. So let me ask the question a little bit better. Is the dominant contribution from ICS or from synchrotron?
Actually, either is possible for the energy 1068.
I see.
Because this actually really depends on magnetization parameter. So that if you think about, I would say that if you think of the corona, then typically people think that the low beta, then magnetization is pretty strong. Usually in this case, I would expect the synchrotron emission down.
I see.
Yeah, but if you allow the general possibilities, I can find the parameter space for the both synchrotron and compton. But if you think about the corona model, like supported by simulations, and the synchrotron model is actually the preferred. But this is model dependent argument.
Do you have any more questions?
So the localization of neutrino sources, like would like a bigger detector help, or is it like more on the modeling side?
The bigger detectors can help if you are interested in higher energy neutrinos. So if you think about higher energy neutrinos, because bigger detectors you can measure track, and right, because track length is actually 1 kilometer, but if you have Gen 2, the track length can be the 10 kilometer, right? And this indeed helps localization. But it's actually pros and cons, because Gen 2 is actually the ISQ Gen 2 are bigger, but it's big, and the separation between the strings has to be larger, and they are not good at observing the lower energy neutrinos. So that I'm not sure that Gen 2 is really helpful to improve the localization for the N1668 bright sources, because the threshold of neutrino, threshold for neutron detection is higher.
You could have like something more localized and something more spread.
Yeah, but this actually costs, right? If you actually dense neutron detector 10 kilometer cubic, yes, in this case, definitely helpful. But of course, it costs more. Yeah.
Okay, so we're going out to dinner with Kohta at 6:30 tonight to Christine's, a French restaurant that we haven't been to. So if you're interested in that, there's one spot left. Other than that, I guess we can all go to lunch now, but let's thank Kohta again.